The fundamental principle of calculus tells us that integration is the reverse process of differentiation. We are happy that when differentiated with respect to x, the functions on the left-hand side of this table result in those on the right-hand side. And so by this principle, we know that when we integrate any of these functions here with respect to x, they will result in those back on the left-hand side. Remember, x is just a letter. We could change x to u and say that integrating the right-hand column with respect to u results in the left-hand functions of u. Whilst this list contains important functions, we are often tasked with integrating more involved combinations than just the functions alone. In this video, we are trying to integrate composite functions. These are combinations such that one function, for example e to the x, is the argument to another function, say sine x. X is replaced as the argument for sine with e to the x, a function within a function. How do we integrate something like this? Well, in general, it is extremely difficult, but there are quite common cases where we can use a trick called integration by substitution. The first case is when the inner function is linear. This means it can be written in the form ax plus b, with a and b constants. To solve this by substitution, we invent a new variable, call it u. Our aim is to manipulate this integral so that it is expressed in terms of the variable u, and hope that it looks like one of the integrals that we know how to do from this table. We are going to set this inner function equal to u. Already, it appears all the x's have disappeared from the integral, but we can't integrate a function of u with respect to x. We need to express dx in terms of du. And to do so, we differentiate our x-u relationship and rearrange. Now we have dx in terms of du, which we can sub into the integral. This constant term here is a byproduct of the dx-du relationship and can just come outside of the integral. This integral now looks like something from the table, and so we can confidently write down the result. This function is in terms of u, and if we want to express our answer in terms of x, we must just sub in from the original relationship. Now I want you to look at integrating this composite function, the argument of cos being x cubed. If we shadow our previous steps and define u as the inner function, relate dx to du by differentiating, and sub back into the integral, we are still left with an unfortunate x term unable to be integrated with respect to u. The linear function was a special case because the byproduct there, found by differentiating, was a constant and did not contain any x terms, and so didn't cause problems in the integral. This here is an issue we cannot avoid, but we can be presented with a way out. This is wordy, but try to take it in. If the composite function is being multiplied by a function with the same form as the differential of our inside function, there will be cancellation. And after we take the constants outside, we have an integral looking like something from the table. Again, we replace u to get it back in terms of x. If instead this were a definite integral, x going from 1 to 4, say, then we needn't change the result of the integral back in terms of x. The integral having a dx with these two limits says that x is the variable of interest and it ranges from 1 to 4. When we substitute in our expression for dx in terms of du, we are changing the variable of interest from x to u. We must change the start and end points accordingly. When x is 1, u is 1, and when x reaches 4, u is 64. These must be the new limits which we substitute in to evaluate the definite integral. Substitution is a method which also works for cases outside of the two here. Often you may be given a substitution to solve an integral. The general plan of action is the same. Express the integral in terms of the new variable, relating dx and du by differentiating, and hope that the integral transforms into something from this table.